let's work some problems involving diodes. Now, I've indicated for problem number 1 that we have a silicon diode in series with our 30 volt source and a 1.5 kilo ohm resistor. We want to find the current through the diode. So, first of all, keep in mind that the anode on the left side of the diode needs to be biased at least 0.7 volts higher than on the other side. So if assuming that's true, then the diode will be on. And once the diode's on, it conducts current. So, and we see that we do have the positive terminal of our voltage source connected to the anode. The negative side is connected to the other side, which would be the cathode. So that means that we are forward biased, since we are providing positive current to the positive side and negative, the negative terminal of the voltage supply is connected to the cathode. So in that case, what we see is that the voltage drop across the resistor would be the difference between the 30 volts we're applying minus the 0.7 volts across the diode. So that leaves us 29.3 volts across our resistor, and that's using Kirchhoff's voltage law. Remember, the sum of the voltage rises minus the voltage drops around a closed loop have to equal 0. So when we add 30, subtract 0.7, and subtract 29.3, we get back to 0. And then, of course, to find our current through that resistor, we would need the voltage drop across the resistor divided by the resistor value. So we know that needs to be 29.3 volts, and we have 1.5 kilo ohms of nominal resistance, which gives us about 19.53 milliamps of current. And then since that resistor is in series with our diode, then our diode current equals the resistor current, which is 19.53 milliamps. And that would be the answer for that one. Okay, so let's look at our second problem here. We're looking this time for V out. Again, we have a silicon diode, and so we know that if it's forward biased, we need to have at least a drop, we need to have a drop of 0.7 of a volt across it. And it looks like below the diode we're at -6 volts, and above the diode we start out with 8 volts at the top. So we're going to see that drop from 8 volts down to 6 volts, down to -6 volts. So that means that, yes, our diode is properly biased. So we have a higher voltage closer to the anode side than to the cathode side. And the difference in that voltage from 8 to -6 is 14. So we've got a 14 volt drop across the whole thing. And so that is going to have to be the voltage drop across both of my resistors is the 14 volts minus the 0.7. So let's talk about what this looks like. So this is V1, and then we've got V2 here. And Kirchhoff's voltage law says that the sum of the currents, the sum of the voltage rises around a closed loop minus the voltage drops has to equal 0. They have to balance each other out. So the way I would write my KVL equation is I would start with my +8 and go around in this clockwise direction, minus V1, because that's going to be a voltage drop. If we've got a current this way, that's going to cause a voltage drop through the 1.2 k ohm resistor, and then the current's going to continue through the 4.7 and down to the -6. Okay. Now the V out over here, this is just a measuring point. there's no circuit over there, so we don't have to worry about the current not continuing from 1.2K to 4.7. Those are in series. Okay, so minus V1 minus V2 will be the next voltage drop, minus our 0.7. And then when we get down to this minus 6, that minus 6 is, it looks something like this if we looked at the source in there. So to get to ground, we're essentially adding 6 volts there, and that equals 0. That may be kind of hard to see, but whenever you see something in the circuit, for instance, you have 10 volts here, a positive 10, you can just replace that with a 10 volt source to ground with the positive terminal at the measuring point. Or if you have a negative 10 volts at this point, that's the same thing as having a remember, this is 0 volts here, and we've got a drop of 10 volts from ground. So you could just redraw the circuit if that makes you feel better, but we're going to add that 6 in here for our KVL equation. So I'm going to move the V1 and the V2 to the other side. They become positive when I do that. So V1 plus V2 would have to equal 8 minus 0.7 plus 6. So that would be 14 minus 0.7, or 13.3 volts across both of those resistors. All right. So we know that in series we can add those two resistors. So R1 plus R2 is the 1.2K plus the 4.7K. I think I wrote that wrong. Should be 1.2, not 1.12. So that should be 5.9 kiloohms of total resistance. So if we want to know the current through those resistors, we would take the V1 plus V2 over the R1 plus R2. So we have a total of 13.3 volts divided by the 5.9 kiloohms, and that should give us our current. So 13.3 divided by 5900 should be about 2.25 milliamps. Okay, now we were asked for V out, not for the current. So how we would find that is, notice that if we start down here at 0 volts and then we're going to drop 6, we get to minus 6 here, which again was our measuring point down here. So we know that there's minus 6 at that point. When we go across the silicon diode, we see a rise of 0.7 in this direction. Okay, so plus 0.7, and that gives us minus 5.3 volts. And then we would add whatever V2 is at this point, because that will get us back up to V out. So how would we find V2? Well, V2 is just the current through R2 times R2. And we already know that that current is 2.25 milliamps. And we know that we've got a 4.7 kiloohm resistor there. So that voltage drop, or voltage rise actually in this direction, would be about 10.6 volts. So when I add this, minus 5.3 plus the 10.6, I get about 5.29 volts. Now, you could have also started on the +8 side of the circuit as well. And what you would do there is have your +8 minus V1, and that would give you V out as well. Now, V1, just like we found V2, V1 would be I1 times R1. Again, the same current, 2.25 milliamps, and this time R1 is 1.2 kilo ohms. Let me write that again. 0.2 kilo ohms. So V1, that would give us 2.7 volts. So if we go back up here, 8 minus 2.7 would also give us about 5.3 volts, which is what we found. Okay, so that was a bit of a review for you of your circuit analysis. Okay, a little bit more probably detailed than what you were looking for. Let's talk about a couple other cases now. What if we have two different kinds of diodes? In problem number 3, I have a silicon diode and a germanium diode. And again, I've got the anode side and the cathode side, and cathode side. Actually, cathode is typically denoted with a K, but since we're just starting out, I wanted to put a C to make that clear, but typically we would use a K for that. Now, the silicon diode, you remember, would have a drop of 0.7 in the forward bias direction. But what about germanium? Germanium is actually 0.3. So I'm going to put that over here too. So that would have a 0.3, I don't know why I keep putting that 0 over there, 0.3 voltage drop when that germanium diode is in the forward bias position. So that means that in order to forward bias both of these diodes, we would need at least 1 volt of potential dropped across both of them. They're both in that same direction, so that's not a problem. And we do have 12 volts supplied, so we're probably good. We shouldn't have to worry about having at least a volt there. Okay, so we're looking for V out. Oh, actually we're looking for the current and the voltage. I think I drew my line in the wrong place there. We're looking for the current and the voltage. So the current through the diodes is going to be the series circuit current from the voltage source down to ground. So again, what we have here is our KVL equation, which would be a +12 minus a 0.7 for the silicon diode minus a 0.3 for the germanium diode, minus the voltage drop across the 2K ohm resistor, minus a voltage drop across the 10K ohm resistor, and that would have to equal 0. So again, the voltage drop across the 12K over here would be 11 volts. So 11 volts would equal the voltage of the 2K plus the voltage of the 10K. And since that's the case, the current through the diode, which is the resistor current, would be that 11 volts over the total resistance of 12K. So 11 divided by 12K, and that would be 9.17 milliamps. Okay, so that's your ID. And then V out is simply the voltage drop across the 10K ohm resistor. So I'm just going to take my current times the resistor value. So I've got 9.17 milliamps of current through 10 k ohms of resistance. So that is, of course, 9.17 volts. Oh, I'm sorry. For the current, I think I miswrote that. It is 0.917 milliamps. 0.917 milliamps. Sorry about that. Let me fix that. 0.917 milliamps. So that gives us 9.17 as our V out. Okay. Okay. So here is a another problem that's a little bit interesting. What would happen if we had two diodes that were in parallel with each other? Now remember, the silicon diode needs a difference of at least 0.7 volts to get past that barrier potential. The gallium arsenide is 1.2. And if you needed these numbers, I would give them to you. The textbook you're working in just focuses on silicon, but I thought I'd throw in some others. So gallium arsenide is about 1.2. So I would need at least a 1.2 volt drop to turn on that gallium arsenide diode. Now, you do know, remember from your circuits, that anytime you have two components in parallel, they have to have the same voltage drop across them. And if we need 0.7 volts across silicon and 1.2 across gallium arsenide, you know, how can we have them different? Well, we can't. That's not going to work. So what does happen is that, as you see up here, we've got 1 volt to work with. And what's going to happen is that 1 volt, we're going to drop the 0.7 across here. And once we do, and this diode comes on, all of a sudden, all of the current's going to go this way, and nothing will be left to go through the gallium arsenide side. Okay, so that will be off, whereas the silicon diode will be on. So if we're looking for I here, I would simply be the voltage drop across the resistor, the 1K ohm, divided by 1K. Now what is that voltage? Well, we start with the voltage we were supplied, which is 1 volt, and we drop the voltage across the silicon, and that's what's left to be our voltage drop across the 1K ohm resistor. So that's 0.3 volts over 1K. Which gives us 0.3 milliamps, or 300 microamps if you want to use that. So what would V out be? Well, V out is simply the voltage across the 1K ohm resistor. So it would just be IR times R, the 0.3 milliamps times the 1K, which of course is 0.3 volts. And keep in mind, we could have gotten there simply by taking our 1 volt that we supplied minus the 0.7. That would also get us a V out of 0.3 volts. Okay, so there's our current and there's our voltage out. Okay, a couple more problems here for you. Let's look at number 5. So again, we always want to look at what we've got going on in the circuit. We've got a positive 10 volts here and a positive 10 volts here. Those are the voltage supplied across the circuit. Now, the issue we have is that since we start out with positive 10 volts, and down here we have positive 10 volts, there's no voltage difference between those 2 points. And we need to have at least 0.7 volts here. Since we don't have that, this silicon diode is off. So if that's off, basically it looks like an open circuit is right here, right? No current is flowing. We would say I equals 0. So in that case, what would V out be? Well, V out would simply be the measure of whatever is at this point here to ground. Okay, and remember this positive 10 looks like a voltage source going to ground. Okay, so there's my 0 volts there, and there's my plus 10. Oops. Plus 10 here. So to get to V out, starting with my ground, we'd have a plus 10. And then we would not have a voltage drop across the 4.7K. Why? Because we've got no current. So V out is simply plus 10. We would look at that 4.7K ohm resistor as if it's just a wire. All right, so now let's look at a different case. Just kind of an interesting problem here. So we've got these 2 silicon diodes, and we've got 2 different inputs supplying voltage to each of those diodes, and then we're looking at one output coming from both. So let's just talk about this. Let's talk about these 4 cases here. What if I have 0 volts applied to each? Okay, so let's just say we've got 0 volts here and 0 volts here. Well, we know we've got 0 volts here. So 0 volts at A and B would not be enough to bias either of the silicon resistors, so they would be off. And then V out would simply be measuring ground because there would be no current anywhere. So that would just be 0 volts out there. Now the second scenario, what if A is 0 volts but B is 5 volts? Well, if B is 5 volts, that is going to turn on this diode here. And we're going to drop our 0.7 across there. And then V out will just be the output, or 5 minus 0.7, which is 4.3 volts. Okay. Let's look at the next scenario. Let me get rid of this. So the next scenario is if we have 5 volts at input A and 0 volts at B. So again, the 0 volts is not enough to turn on the diode at B, but the 5 volts at A is enough to forward bias the diode there. So again, on the other side, we would be at 5 minus 0.7 or 4.3 volts, and that is also V0. Okay, so this is the diode at A is on, and this is the diode at B is on. Okay, so what happens for our final case? Let me get rid of this. What happens for the final case where both A and B are biased at 5 volts? Okay, so we've got a plus 5 volts here and a plus 5 volts here. Well, that's going to turn on both of the silicon diodes. So we're going to have that drop of 0.7 here and the drop of 0.7 here. Unfortunately, they are, of course, the same voltage. So at V0, we would have 5 minus 0.7 or 4.3 volts. So again, 4.3 volts. Both diodes are on. Now, you might have seen something that looked a little bit like this before, and I want to call your attention to it. When you have two inputs and an output where both can be off, one can be on and one can be off, or both can be on. And then for the output, you have 0, and then when both are off, and then you have a 1 or a high voltage when either of the inputs is on. And that's like your OR gate from digital. And this is one way we would make an OR gate. So I just kind of wanted to point that out to you, that this is indeed something we would use as an OR gate. We could also fashion AND gates and everything else. And typically gates are made with transistors anyway. This is just a different way of looking at it. But I did want to show you that a lot of your digital circuits actually come from the semiconductor work that we're doing right now. Okay, so I hope this video has helped. If you have any questions, as always, just ask me the questions when you get a chance.